Okay, so is my screen is visible to you? Say yes or no.
Yes, sir.
Okay. So in the previous lectures, we saw the BJT part. Okay. Actually, there are many types of transistors in use, like based on their applications. Transistor can be classified into two parts. So here we will see first the classification. Classification of transistors. First one is BJT that we have already seen. And in the two parts we saw, but one is NPN transistors we saw, and another one is PNP transistor we saw, right? Now, another part is called as the FET, field effective transistor. In that also we have two parts. One is junction field effect transistor, and another one is MOSFET, metal oxide semiconductor field effect transistor. So this part we have already seen, BJT part we have already seen or covered. Now in today's lecture we will start FET, that is the field effect transistor. Okay, so we started with classification of transistors. On that, bipolar junction transistor was one part, and the second part is the field effect transistor. In the field effect transistor, we again have two parts. One is the junction field effect transistor, JFET, and the MOSFET is the metal oxide semiconductor field effect transistor. So let's start with FET. Okay, field effect transistor. It is a voltage control device. Voltage controlled device. That is the first thing. Whereas BJT was the current control device. Some advantages are there, like it provides high input impedance. Input impedance. And also it require less power, or you can say low power consumption was there, low power consumption. So I am telling the advantage why we are going for the FET. Because of these some properties make FET better than your BJT. And most important thing, it is a unipolar device. Unipolar device. What is the meaning of this unipolar device? Means here the current will be carried only because of majority carrier. Majority carriers. The current carrier will be only the majority carrier. It will not be carried by the minority carrier. Okay. Not carried by minority carrier. As we saw in BJT, there the current was carried by majority and the minority carrier, and there, as we know that in the minority carrier there is a large effect of temperature was there, right, in BJT. But here, as there is no current carried by the minority carrier, there is no effect of temperature is also there. Okay, and the gain is characterized in the transconductance that we will see in detail. So we will start just like in BJT. If you remember, we was having the three terminals. One is what? Tell me the three terminals of BJT. Anyone?
Emitter base collector.
Emitter, collector, base.
Yes, emitter, collector, and base was there, right? Here in the FET, we again have a three terminals. In FET, we have three terminals. Okay, and it is represented by straight lines like this, where source is equivalent to emitter. Emitter and source are equivalent. So here we have a one terminal called as source, which is equivalent to emitter. The terminal which is equivalent to collector is drain. It is called as drain. And Just like base, we have a gate terminal here. Okay. So the current will start from source to drain. That means it will flow from source to drain. And it is affected by the gate terminal. Whatever voltage you will provide in the gate terminal, it will affect your current. But the current will flow from source to drain only. So it is similar, that collector is similar to drain, emitter is similar to source, and the gate is similar to base, like that, right? So if I discuss about the source terminal in FET is one through which the carrier enters the channel, okay? Through which the carrier will enter into the channel. And this is analogous to emitter. The source terminal can be designated as S. Okay, source will be designated as S. And the current entering the channel at source terminal is indicated by IS. The gate terminal in the FET plays the key role in function of FET by controlling the current. Okay, so this gate terminal will control the current through the channel. By applying the external voltage here in the gate terminal, the current can be controlled. And the gate is a combination of two terminals connected internally that are heavily doped. And it is, of course, analogous to base. Now, in drain terminal, I'm telling you about the drain terminal. This terminal, that is the third terminal in FET, is one through which the carrier leaves the channel. Okay, so it will start from the source, it will leave from the drain, and it is controlled by the gate terminal. Okay. Now, as we have seen, FET is of two types. One is a JEFET, or you can say junction field effect transistor. Another one is MOSFET, metal oxide semiconductor FET. So let's start with JEFET first. So I'm starting junction field effect transistor. That is called as the junction field effect transistor. It's just like a normal FET. Okay, this is also called as the normal FET. It is of two types. One is called as the N channel, another one is P channel. So in JFET also we have two parts. One you can assume it is an N channel, JFET, N channel, junction field effect transistor. Another one is the P channel, JFET. So what is the difference between them? That I will tell you. Okay. So if I talk about the N channel JFET, for this what we will do, I will take the P type of material. Okay, I will take a P type material here, P type substrate. It's called as a substrate. Okay, and in that, what I will do, I will create the channel. Okay, so in the N channel is mostly used for the fabrication, and the 1 minute, and just I'm removing this part from the N channel. I will start. Okay, yes, from here. So I am starting N channel FET. So here what we will do, we will take a narrow bar of, like this, I will take one narrow bar of N type material. Okay, as this is N channel FET, so I am taking one N type bar. And then what we will do, we will dope a small part portion here with P type material. It's a highly doped material. It's called as P plus. Okay, here with some ohmic contact here and here, we can make the two terminals. In case of FET, you can interchange the position of source and drain. They are same. But in case of emitter and means in case of BJT, we was having the emitter and collector and their manufacturing is different. Emitter was highly doped and the collector is moderately doped. Collector is of large size, emitter is of moderate size. But here, what is there? Source and drain are same. So you can interchange the position of your source and drain. And here in this terminal, you have to connect your gate terminal. So here you will connect your gate terminal. This will be your gate for controlling. This you can assume as source and this you can assume as drain. Okay, so this will be your source, this will be your drain. As there is an N channel in between them, there is an N channel in between them. It is called as the N channel FET. Just opposite, you can assume if you are taking the P type bar and you are doping with N material here like here, and this is your drain, this is your source. In that condition, that will be your P channel, right? Just so they are similar. So I will explain only the N channel. Just same thing you can study with the help of P channel. Okay. So let's see the procedure. Okay. So what you have to do, you have to take the narrow bar of N type semiconductor on which P type material is formed by the diffusion. With the help of diffusion, you made this P type diffusion. And there are two sides joined by the line, okay, for the gate terminal. Now, the area between the gate is called as the channel. So this is called as the channel. This will be the channel. Hence, the cross sectional of FET can be understood by this. And here we are adding one ohmic contact. So this is ohmic contact. Now we will see the operation. So let's see. I'm just drawing the same thing here. Here we have a p-type material. We have a p-type material. Okay, and connecting like this. So both the terminal of gate you have to connect like this, and you can provide here. Suppose this is VGG, that is the gate voltage, and in between this you can add. This is your source. This is your drain, and in between them you can provide one voltage source that you assume as VDD. Okay. Now in the first case, what actually I'm assuming that the first terminal is this input terminal is or the voltage which is connected in gate. The gate terminal voltage we are assuming as a reverse bias. Reverse bias, do you know, right? And we are saying this we are not applying in the first case, case one, we are not applying this VDD. I am applying the reverse biasing only. So what will happen? Here I will apply this negative and positive like this, right? Negative to P terminal, what it will do? It will increase the depletion region, right? This it will increase it because this negative will repel the hole which are in majority carrier in this direction, and it will increase this depletion region, and it will expand. It will expand. Okay. And if for example in the second case, I told you if my VGS or VGG is reverse bias. So what will happen? The layer, depletion region will rise. Okay. In the second case, what I am assuming, case two, I am applying only the VDD. Okay, that to positive, negative. For example, I am applying like this. So what will happen? I'm just changing the color so it will be easier to understand. For example, I'm applying here a forward bias. I'm not applying anything here. Okay, I'm not applying here. Only I'm applying the VDD here. So what will happen? This positive will attract the electrons, right? This positive. This was N channel. Electron will move like this, right? Electron will be attracted, and this will repel, right? So as you increase this VDD, the movement of electron will increase, and which actually flow the ID. So even if you are not applying VGS, some of the current will flow, because as you increase the value of VDD, the electron will start move from source to drain. Okay. And for example, now in the third case, I am saying both the things you are applying, both the terminals you are applying. That means you are applying the VGG as a reverse bias, and you are applying VDD in a forward biased. So what will happen? See, as you apply the forward bias first, so the electron start moving like this, okay? And as you are applying the reverse bias, this depletion region will increase, and it will restrict the flow because the channel width will reduce, right? Channel width will reduce. This process of reverse biasing, as you are increasing, it will increase the depletion region like this. And what will happen? One pinch off condition will come where the movement of electron will be restricted and it will not flow further. Okay. So because of this gate terminal voltage, you can restrict the flow, or even you can provide the energy to flow the electron. So if it is reverse bias, that means you are restricting the flow, and this process where your VGG is negative or reverse biased, where VGG or VGS is reverse biased, this process is called as the depletion process, depletion region or depletion process, depletion mode. Okay, so here the depletion layer plays an important role in the operation of FET. That's why the name depletion, as you are applying the reverse bias, and the P region that was there, here depletion region is increasing, and this depletion region plays an important role because it's actually changing the width of channel. That's why it's called as the depletion mode. Okay. And there is a certain, as I told you, if you are increasing the voltage, reverse bias voltage, so this depletion width will come near to near, and one condition will come where this both the depletion region literally touches each other, and this voltage is called as the pinch off voltage. Pinch off. And since the gate voltage is controlling the drain current, this FET, as you know, if we are applying the VGS, and this gate voltage is controlling this process. That's why it is called as the FET is called as the voltage controlled device. Voltage controlled device. That is the first thing that is very important. Okay, now what is the knee voltage? When now we will see what is the knee voltage. Knee voltage. When you're not providing, when VGS is equals to 0. When VGS is equals to 0. That means what? There is no depletion region. You are only applying the VDS. You are only applying the VDS. And no VGS. We are not applying any VGS here. VGS is equals to 0. So what will happen? As you are increasing the VDS, the more number of electron will flow, and you will get the output. Right? So when your VGS is 0, and they are shorted, the current from source to drain is also nil, as there is no VDS. Now, as the voltage between VDS is increased, the current flow ID from source to drain increases, and this increase in current is linear up to a certain point. Okay, so what will happen if I draw the characteristic of it? Okay, this is what ID, and I am saying this is VDS. So what happened? As VGS, I am assuming 0. Okay, and now I am increasing the value of VDS. So it will increase linearly, because as you are increasing the VDS, more number of electrons are moving like this. Okay. But what will happen? It will increase only up to the knee voltage. Up to this voltage is called as the knee voltage. Knee voltage. And after this, if you increase, what will happen? The resistance will also increase because of the movement of electrons and because of the repulsion and attraction here. Resistance will increase. That will what it will do? It will saturate the current. After this knee voltage, the current will not increase, and because this portion is called as the saturation region. Saturation region. So here, if even if you increase your VDS value, this current ID will remain constant. Okay. So this is called as the drain characteristic. And this is when VGS is equals to 0. Now what we will do, we will reduce the value of VGS in the negative biasing. So negative biasing, that means here I am applying the negative. VGS is equals to -1, for example. So here it will increase the depletion width, that will reduce the channel width, and the drain current will reduce. So it will be similar, only it will be like this. And this is for VGS is equals to -1. If you further decrease the value of VGS, you will get like this. If you further decrease the value of VGS, so VGS is equals to -2 or -3, like that. So this is called as the drain characteristic. Drain characteristic. Okay. So in the drain characteristic, you have to keep your VGS constant. If you are increasing the value of VDS, there will be a linear curve up to a knee voltage. After this, if you increase, this will be the pinch off position and the current remain constant in the saturation region. Now, we will see in detail about the MOSFET part also, and then we will go for the numericals. So there are some disadvantage in the JFET. So that was a junction field effect transistor. And now we will discuss about the MOSFET. So in the MOSFET, it stands for metal oxide silicon field or semiconductor also. It's called as metal oxide semiconductor, or sometimes called as metal oxide silicon. So you can assume semiconductor, that is better. So metal oxide semiconductor field effect transistor. Okay. So one problem is that in JFET, it was only in the case of depletion mode. Okay, there are two mode that we know. One is called as the depletion mode. Depletion mode. Another one is called as enhancement. Enhancement mode. So in the depletion mode, we have to assume the gate terminal is negative or reverse biased. Reverse bias or negative. In case of N, I'm telling you, okay, so here you assume reverse bias. Here the depletion width will increase. In the enhancement mode, VGS should be positive. Okay, so and that will reduce your width of depletion region. That is the basic difference between depletion mode and enhancement mode. In case of JFET, in case of junction field effect transistor, only depletion mode is possible. But in case of MOSFET, both the mode are possible. That's why we are moving towards the MOSFET, because here you can go for the depletion mode and enhancement mode in a single device. So what is the construction of a MOSFET? Construction is similar to FET, but only what will happen, I'm just drawing it. Okay, here I'm drawing the N channel. Again, N channel MOSFET and the P channel MOSFET will be there. N channel MOSFET. In the N channel MOSFET, you have to take the P type substrate here. P type substrate. Okay. In that, you have to diffuse the N positive terminals like this and positive terminal like this. And in between them, because of diffusion, N channel will create. N channel. It's called as N channel. So it's a diffused channel. It's a diffused channel. With the help of here you have to make one SiO2 layer. SiO2 layer you have to assume. And here you can make a ohmic contact with silicon, source. Here you make a drain terminal by connecting these two. This will be your gate and this will be your drain terminal. So this is the construction where you, for the N channel, you have to take the P-type substrate. Then here you have to make a diffused N plus and N plus region. In between them, diffused channel you have to create. And here, as I told you, here you have to make the SiO2. That SiO2 is just like an insulator. Why are making like this? Because here you have an N channel, right? Here you have a silicon dioxide. Here you have an ohmic contact. This is ohmic. So it will just behave just like a parallel plate capacitor. In the parallel plate capacitor, we are having the two plates in between. We are using the dielectric, and with which will dielectric, which will behave as a capacitor. Okay, so here because of this, we are using like this. Now we will see the depletion mode here again. So working of this N channel here, as we saw in the case of FET, if I draw a MOSFET here, you can assume this is the P plus and this is gate terminal, this is the source terminal, and this is the drain terminal. Only a single difference is there. Here you are making the ohmic contact. Okay, and between the gate to source, you have a VGG, and between drain and this connected to a source, and this is connected to like this VDD. The process is again same. Okay, when no VGS is applied or no voltage is applied across this gate terminal, okay, some current flow due to the voltage between drain to source. Okay, and the minority carriers, if you are suppose applying the VGS here, like negative to positive, so negative will attract the holes, right? Negative will attract the holes which is in the minority carrier here. Same thing, as we are increasing the VDD, more electron will flow from here to here and the conduction will happen, right? And because of the gate to source terminal, here also it's connected, right? So it will increase the depletion layer and this process is almost same. There is no difference. Only here, as you can see, the gate terminal was connected, but here its gate terminal is separate and this terminal is different. So for this, we will do one thing. I am just explaining you the characteristic of it. Characteristic is more important. So let's see the characteristic of this MOSFET. So here we have a drain and transfer characteristic. So characteristic. First, we will start with drain characteristic. In the drain characteristic, the graph will be between ID versus VDS, the voltage across the drain to source, where VGS is
Sir,
constant.
can you explain the construction of N channel again?
Yes, yes. In the N channel, 1 minute. So in the N channel, okay, I had already made the figure. Okay, so here is the N channel. That was only the representation that I showed you. So in the N channel, what you have to do, you have to take the P-type substrate. Okay, in the P-type substrate, you have to diffuse the N positive material. Because of this, one diffuse channel will also generated because of diffusion. So here you are having N plus, and in between you have a N channel. It's similar to that of junction field effect transistor, if you remember. There we was having the source and drain, in between we was having the N channel. So only the construction is different, but the process is same. And the second thing is what here we are making here you are creating the silicon dioxide insulator, which will behave just like a dielectric. And if you remember a capacitor, we are having the two parallel plates. In between them, we are having a dielectric. Okay, so it will behave just like a capacitor for storing. Now, if you see the process, what is happening, it is similar to that of your FET. That means as you are increasing the, okay, here if you see, if you remember, if you are not applying any VGS, if you are only applying the VDD, what will happen? The electron, as this is N channel again, okay, N channel, as you see, this is N channel, right? But a diffused channel. So what will happen if you are applying positive here, negative here? So the electron will be get attracted in this terminal and it will be repelled from this terminal. So as you increase ID, the drain current will flow, right? Now what will happen if you apply the VGG in a negative, like reverse bias, it will work in the depletion mode, as I told you. So I'm explaining only the depletion mode. So in the case of depletion mode, what will happen? This depletion region will increase and that will reduce the channel width. As the channel width is reduced, the current will also be reduced. Now, in the enhancement mode, in case of enhancement mode, what is the meaning of enhancement mode? When you are applying the positive across it. So if you provide the positive across it or a forward bias across it, positive here. So what will happen? This will be forward bias. As this is forward biased, the depletion will width will be reduced and the more channel width will be it will get. The electron will get more channel width to flow. So what will happen? The current will increase. So to better understand, I'm drawing the characteristic and through which I will explain the total process here. So if here we are having the two type of characteristic, one is called as the drain characteristic, another one is called as the transfer characteristic. Drain characteristic is plotted between ID and the VDS, where VGS is constant. And as you know, ID is the output current, VDS is the output voltage. If you remember this, okay. So here we are having the drain, here we are having the source, here we are having the gate terminal. Okay. So here we are applying the VGS, here we are applying the VDS, and the drain current is flowing like this. So if you are draw the plot between the output current and output voltage, by keeping the input voltage constant, that is VGS, it is called as the drain characteristic. So if you see, if I'm saying, for example, keep the VGS is equals to 0. I'm saying VGS is equals to 0. So if VGS is equals to 0, here I'm trying the peak terminals, right? FET and JFET are almost same. Here only one terminal will not be there. Just I'm drawing here. So here is suppose P. Okay. So as I am saying VGS is equals to 0. VGS is equals to 0. So there will no depletion region. As you increase the VDS, this is VDS, the drain current will also increase. More number of electron will flow. This is positive or negative. Okay. So it will attract the electron and the more current will flow. So what will happen? It will flow like this, linearly. Okay, what will happen in this point? Because of internal resistance, as the electron is moving fast, because of this internal resistance, it will also increase and it will saturate the current. And after this point, after the pinch of voltage, it will remain constant. This is the point when VGS is equals to 0. Now what I am saying, you decrease or take the negative value of VGS. So what will happen? Because of this negative voltage, the depletion width will increase. That will reduce the channel width. And because of that, the ID value, that is ID value in milliamps, will reduce. Okay. In a similar fashion like this, and it will be for VGS is equals to -1. Okay. Now, if further I draw like this, it will be decreasing as the width is increasing. So VGS is equals to -2. Again, if you decrease the value, it will be VGS is equals to -3 and so on. And when you will decrease, the VGS is equals to -6, it will come near to 0. So when you reduce to -6, it is called as a pinch of voltage, VP. Okay, it's a pinch of voltage. Pinch of voltage means what? When you reduce the value of VGS in the negatives, the width of this depletion will increase so much that it will close this channel width, and after this, no current will flow because the electron movement will be restricted after this. Okay. So what I drawn, this was your drain characteristic. This was your drain characteristic. Okay. Now I'm drawing the transfer characteristic. For this, I'm just changing the color so it will be for us. Okay, so this was your drain characteristic. Now I'm drawing the transfer characteristic. So here I will explain. So transfer.
Sir, both drain and transfer characteristics are like for depletion mode.
No, see, as the VGS is negative, so this is depletion. Okay. For example, if you increase it to positive, VGS is equals to +1. So what will happen? The width will reduce. Okay, width will reduce, and the more current will flow. It will get more channel width. So in this case, when VGS is positive, this on positive means VGS is equals to +2 or +3. This values, for this value, it is called as the enhancement mode. So in the same graph, you can make both enhancement.
Okay,
So,
sir.
okay, so when VGS is 0 or negative, it is depletion mode. If VGS is positive, it is called as the enhancement mode. Now, in the transfer characteristics plotted between ID versus VGS, and for fixed value of VDS. VDS is fixed. This is what output voltage, output current. This is output voltage, and VDS is, sorry, input voltage, and this is output voltage, right? So now the transfer characteristic is plotted between the output current, input voltage, where we are keeping the output voltage constant. So you can draw the transfer characteristic with the help of drain characteristic. Okay, so here you have to take the VGS. Here you have ID, and you have to keep the values. Okay, so here you have to take the positive values. Here you have to take the negative values. And just rub it because it will be good for us. Okay. So I am drawing so here what I will do, because we have to take the VGS is equals to negative, that's why I drawn the graph once again. Okay, so here this will be +1, this will be +2, this will be +3, this will be -1, -2, -3, -4, -5, and -6, because at -6 it will be a pinch of voltage. Okay, now parallelly you draw the lines. Parallelly you draw the lines. Okay, for this also you make the parallel lines like this. Parallel lines this. My graph is not looking good, but you can make by your own. I'm just telling you the process how to make it, right? So you have to make the parallel lines like this. This is for the VGS is equals to -6. So -6, the value of VDS is equals to 0. So you can keep it here. For example, for VGS is equals to 0, the value of ID is this one, so it will be like this. If you plot for VGS is -1, you can make a constant line here. You can assume this is VDD, and for this you make this one. So wherever it cut this line, you make here. So it will come like this, increasing. This the current you will get at VGS is called as the IDSS. Okay, it's called as the IDSS. IDSS. What is this IDSS? It is the maximum drain to source saturation current. Saturation current when VGS is equals to 0. So it's a maximum drain to source saturation current, DSS, when VGS is equals to 0. It's very important part. Okay. So when your VGS is equals to 0, the current that you will get the maximum, it will be VDS. Now, if you increase it further, that means this was your depletion mode. Depletion because we have taken the VGS negative. If VGS is positive, it will increase further like this, and this is called as an enhancement. So in the enhancement mode, the minimum value of current is IDSS. In case of depletion mode, the maximum current is IDSS. Understand? That is the connecting point between the depletion mode and the enhancement mode. Understand the concept? Right.
Sorry, sir, could you please explain that again? The IDSS thing.
Okay, IDSS. See, when VGS is equals to 0, okay, in this, whatever current you will get when VGS is equals to 0 is the maximum saturation current. I'm not talking about this change, linear current. No, I'm talking about the saturation current. So whatever saturation current you will get when VGS is equals to 0 is called as the IDSS, drain to source saturation current. And as you know, VGS is equals to 0 is not come under depletion mode. It will not come under the enhancement mode. It is a connecting point. So we can say IDSS is maximum current if you consider the depletion mode, and it is the minimum current because now after this it will enhancement mode will start after IDSS. So this IDSS is the minimum current for the enhancement. Understand?
Okay, sir. Got it.
Okay. So the equation that we will use for the enhancement mode, and for the depletion mode is different. Depletion mode. So in case of enhancement mode, the value of the drain current will be equals to K VGS minus VT, threshold voltage, and K is again a constant. K is constant. VT is the threshold voltage, is also constant. And in case of depletion mode, the value of drain current ID will be equals to IDSS 1 minus VGS by VP whole square. So if I say the rate as a depletion mode current, the rate of change of current, if for example you have to find out the value of ID rate of change of current with input voltage. That means if you are changing the VGS, what is the change you will get in ID? So you can do one thing, you can differentiate both the equation by VGS. So if you differentiate VGS, so what you will get? You will get 2K VGS minus VT. I think so. It's correct, na? If you differentiate with respect to VGS, and if you differentiate, for example, this one. So del of ID by del of VGS is equals to 2 IDSS divided by VP. Divided by VP, 1 minus VGS by VP. And here you can do one thing, you can take the VP common, so it will be 2 IDSS divided by VP square VGS minus VP. So this is the rate at which they are changing with respect to VGS. Okay, so these are the two formulas that we will use to solve the equations and for numericals. So let's see one numerical at least for today's lecture. Question
what
1.
is VP?
VP is the pinch of voltage, and it is equals to minus of VGS. That I will explain during the numericals. Okay, so this pinch of voltage is what? A voltage that you are applying, that you saw, na? This pinch of voltage, where pinch of voltage, what VGS at minus 6 is the pinch of voltage where you will get the drain current equals to 0.
Yes, sir.
Okay. So now in question, what they did, they have given the transfer characteristic like this. They given this is 12 milliampere. This is the value of ID. And they said this is minus VGS. This is minus 5. They said write down the equation for drain current. Equation for drain current. So as I explain you that first thing you have to keep as the VGS is negative. So it is working in which mode? In which mode? Depletion or enhancement mode? Which mode? Anyone? It is in the depletion mode. Why? Depletion because VGS is negative. So in the depletion mode, which equation you have to use? This equation. What is that? ID equals to IDSS 1 minus VGS by VP whole square. Okay. The second thing is what? What is the value of IDSS? IDSS is the maximum current drawn in case of depletion. This is your IDSS. Okay, so I am just writing here that is 12. 1 minus VGS. We don't know what input they are providing, so I'm writing like VGS only. Now VP, that is the pinch of voltage. Pinch of voltage when the drain current is 0. This minus 5 is the VP. This is the pinch of voltage. Okay, so you just write down minus 5 here, whole square. So just you can write down 12 1 minus or plus VGS by 5 whole square. This is the value of ID. Understand? Now you see the second question. For example, they are giving IDSS is equals to 32 milliamps. And they gave VGS offset is equals to minus 8. VGS is equals to minus 4.5. And they said find the value of ID. So from here, what is the first thing that we remember is what? As the VGS is negative, it is working in the depletion mode. And in the depletion mode, as I told you, the formula that you have to use is IDSS 1 minus VGS by VP whole square. Okay. Now question is, we don't have the value of VP. The VGS at offset is a pinch of voltage VP. So VGS at offset is called as VP and you can assume as VP. Now IDSS is 32 milliamps. 1 minus VGS minus 4.5 and VP is minus 8. So like that, you can find the value of ID and tell me the value of ID from here. Everyone, try this question and tell me the answer.
milliampere.
Yes, 6.1 milliamps. Okay, so that is your drain current. We will see some more question and numericals based on this in your next lecture. And for this, I am sharing your notes. Have you uploaded your digital assignment in Moodle? Please check it.
Yes, sir.
Yes, sir.
Sir,
Yes.
so VGS offset is the same as
Pinch of voltage.
voltage.
Yes, yes.
Okay.
Okay, so that's all for this lecture. I will take the attendance directly from here. If you have any doubt, you can ask. Okay, thank you. Thank you so much.
Thank you, sir.
Thank you,
Sir?
sir.
Yes.
Sir, can you send the assignment answers?
Yes, yes. So
Oh, okay, sir. Thank you.
Thank you, sir.
thank you.
Thank you, sir.
Thank you, sir.
Thank you.